this Google presentation.
Fantastic.
I use Zoom.
Yeah. John and Sridhar also joined.
Yeah,
I just joined.
How are you?
I'm doing good. Thank you.
Welcome.
Whether the slides are changing or not, you can.
Yeah, good morning, good evening. I guess for you, Sridhar, it's pretty, no, it's not as late as it is for me. It's 11 p.m. for me, only 8 p.m. for you.
Yeah, right.
Okay. So, would you like to see if slides are starting? Can you please? Would you mind? Yeah, it's coming down very well. Yes.
Mic बताया
Okay.
mic
Okay.
mic on ಮಾಡಿ
Can I start now?
Sure, whenever you guys are ready.
Yeah, so good morning to those who have attending physically here, and good afternoon to Sridhar, and good evening to John, and so welcome to this session, second day session. We have very important presentations today. So I don't want to take much of the time. I want to very briefly say only 2 sentences about Professor John Scully, and those who are in the corrosion field, he doesn't need an introduction. I would like to say that he is a world leader in corrosion, science and engineering, working on a very broad topics in all of them in depth. And he is also the chief editor of Corrosion Journal. Earlier it was called NACE International, now it's called AMPP, which is a very, very renowned journals in the area of corrosion. And with this brief introduction, John, it's your time. It's about 30 minutes. If you can give about 5 minutes for questions, it'd be wonderful. Thank you very much. I welcome for your presentation.
All right, good morning in India there. It's a pleasure to be here at this workshop on corrosion asset integrity. My thanks to the Indian Institute of Science and the organizers, BS, and I'd like to really say that I'm honored to give this presentation. Today, I'll be talking about the role of universities in corrosion mitigation and about corrosion centers that are university-based, which we have one here at the University of Virginia that's operated for, well, since 1969. And so it's gone through many generations of students and a couple generations of faculty. Let me get right to it, though, and talk to you about what our perspective is on the roles of universities in corrosion mitigation. And so without further ado, I'll go to the next slide. So what I'm going to address as requested is how can industries, including defense infrastructure, others, oil and gas, et cetera, I won't name them all, benefit through establishing of university centers, let's say, of excellence in corrosion. And there are many universities in India that do excellent research, and I'm always impressed by VS's work and everybody's work that I see. And encourage people to submit papers to the Corrosion Journal also from India, because they're always excellent. We have editors in India, I want to mention too, on our editorial board. One of our associate editors is Prof Gore in India. And so we'd like to have a closer relationship. But anyhow, onto this topic. So how do we sustain and establish a center of excellence in corrosion? And I'll give some existing centers in corrosion. You know the good ones. There are ones like that are excellent, like the Fontana Corrosion Center, and I'll say a word there. So we'll end with the path forward and how to create an academic center for corrosion excellence. And I hope to finish this in about 25 minutes and leave time for questions. Okay? So the outline here is what are some typical approaches that industry and government use when they decide to do research with the university, and usually there's short-term, long-term needs. Some of the ultra short-term needs, probably the university isn't the best venue to do that research, although we have postdocs and research scientists that can do pretty fast response. But our long-term research educates PhDs and puts the future Narazi Sridhar is not these replaceable, and especially with that 40 years of experience he has, but basically to produce PhDs that can have impact and go in. And I have to tell you, on every project that I've done with industry, and there are a lot of them, as I'll give you a list, short term, whether the project's short or long term, I'm just saying, like say short term after the project's completed, it's always the technical issue, the technical content that's the most important to the customer. But you know what? after 10 or 20 or 30 years, you know what's the most important? You got it, the person that we delivered, the PhD level person. That's the most important thing. That's our product, besides the research. And it's a very important one, maybe more important if they go through a career and become very experienced. So anyway, we'll give some examples in industry, some examples of government university collaborations, and we'll talk a little bit about our Center for Electrochemical Science and Engineering at UVA, and how you would form a Center of Excellence in Corrosion. And so some typical approaches that industry and government use, and this is kind of borrowed actually from one oil company that didn't want to be named, but it's a pretty typical approach of how you decide. First, people decide whether it's long-term or short-term research. And so the flow chart kind of goes like this: like you observe in the short-term funding stream, you observe the industry, the oil company observes corrosion problems related in their current operations, and there might be short-term funding for solutions that's really more of operational funds, let's say, or from production if it's the front end or the back end production, or the oil field type work. And they have operational expenditures and capital expenditures. They might use both or one or the other in some decisions made as to what to do. Then they approach the university R&D, and then the problem is solved in the short term. The best way for us to man that problem, to provide information quickly, is with postdocs. So we use postdocs and some research scientists, and we blend that in with some undergraduates at UVA, but we mainly use those because they can be dedicated to the research. And the problem is resolved. Some of those are typically, are short-term projects, like 1 year. So the challenge is to decide whether and when to use a long or short-term approach, because if you've got something that's a sort of takes 3 years to solve, maybe this 1 year approach is not the best. And then so that brings us to the long term. The long term has some differences, though, as industry tells me, because that's either observed or maybe even anticipated corrosion. For instance, they might go into a new harsh environment, or be using new materials or a new process, some change in chemistry, say it's a chemical process industry, and there's some change in operating temperature or operating chemistry. And so it might actually be an anticipated corrosion problem in a future operation. It might be an observed observation for some sort of long-standing issue. And so there's long-term funding. They know it might take more than 1 year to provide a solution, more than a few months, maybe a couple of months. Our typical PhD after a master's degree is 3 or 4 years at Virginia. So it's pretty long, but only about the first year has to be dedicated to classes. We give a fair number of classes in the U.S. in graduate research. Typical material science departments requires 8 classes for a PhD. So that first year they don't get much research done, but then it's 3 good years of research. And so you see there the blue path and the pink path, and one is what government does, and those are acronyms. Pardon me for the acronyms, but like DOE is Department of Energy, et cetera, Department of Defense, DOD, National Science Foundation, and Department of Transportation. And often they're a customer. They're not really they maintain some equipment like the infrastructure or like the Navy, and that they're responsible for maintaining equipment assets, let's say, and they might need to deliver novel scientific understanding or technology. For instance, if it's new alloy or new material, or new aircraft, or even some mandate like elimination of chromate, they might have a 5 or 10 year study, and it's long term. Usually never runs more than about 7 or 10 years. We have had some long collaborations with industry, and we can talk about that. I'll give you an example coming up next in the slide deck. But the problem can be resolved typically in, say, 3 to 5 years, or at least that's what you're shooting for. We staff that in various ways at UVA. It doesn't mean it has to be staffed for the duration of the PhD. We have different approaches, combinations of postdocs and PhDs and master's students and even undergraduates, that we put the orchestra or band together to solve the problem. So the challenge is kind of here to decide where the money comes from, and everybody's got a problem, right? It's the matter of which percolates to the top and decide whether to use short or long-term funding. What's an example of that? I'd like to give a broader example. And the first industry university example I'll give is actually not what you think of in corrosion all the time, but it's the Rolls-Royce. It's because it's a very impressive approach. It's the Rolls-Royce University Technology Center, so UTC. So as you know, Rolls-Royce is an aircraft engine manufacturer. You know, one of only a few, General Electric and United Technologies, Pratt & Whitney, and Safran. And there really aren't a whole lot more than that. And so Rolls-Royce is a major supplier. And as you know, it's a $500 billion a year business, jet aircraft engines. And you know, they have hot corrosion problems. And they have more corrosion problems as you get volcanoes, et cetera, like happened in Europe a few years ago. Or obviously if you go into some harsh environments like in the desert. So they have 23 UTCs indicated in blue. One's in Charlottesville, Virginia over there in blue. I don't know if you can see my cursor, but over there in the US in blue. And then 6 green research centers. And each center addresses a key technology, and collectively they tackle a wide range of engineering disciplines. So ours is naturally in oxidation and corrosion. And then the consistent strategy of developing long-term relationships that has provided Rolls-Royce with close contact to world-class academic institutions and given Rolls-Royce access to a wealth of talent and creativity to help really maintain their capability and their market share into the future. So, you know, here's an example of a system, and some of the projects are listed there in the gray box. Ceramic matrix composites. You know, some of the engine components are going towards CMCs. They're called CMCs, ceramic matrix composites. EBCs, environmental barrier coatings. And, you know, there's the case where if you take sand in your engine, that can form a eutectic with some of the materials that you use in your engine. And that's a low melting phase. It's a no melting, as you know, and so it can be be problematic. There can be alloy corrosion, hot corrosion, combustion analysis. Also, some things that you don't think about in corrosion, like isophobic materials for icing and particle separation. So a good project at UVA, to give an example of, is that environmental barrier coatings were needed to protect silicon carbide-based ceramic matrix composites that are used in engine components. And the EBCs limit the reaction of the silicon carbide with combustion gases and ingested debris, like for instance the sand that I was talking about. So it is a coating for mitigation, but it's not one that we think about in aqueous corrosion very much. So how does technology develop it? First is the technology need at the left. They contract the appropriate UTC based on discipline. They discuss the statement of work. They create a task order with my colleagues at UVA, such as Beth Apila, who does high temperature oxidation. They perform directed research, and then there's transfer of the new science and technology to Rolls-Royce. And the EBCs are a success story, an example where they were studied extensively at UVA, still are. And then they've used some of those environmental barrier coatings in their products. So what are the benefits? Who gets what out of what? The universities sponsor research funding that supports the faculty and the students. We pay our graduate students a stipend, a research assistantship, and pay for their health insurance. Student development, student internships with Rolls-Royce. So the companies get the interns, they get to try before they buy and see who the best student is that they like the most. Publications and patents. Professors required for tenure, as you know. The industry benefits too, the access to the technological experts, the access to the state-of-the-art research tools, workforce development, and patents. So what's an example of government university collaboration? One of the biggest over in the United States over the last 10 years, it's pretty much into its last year, and it's winding down after about 12 years, is the Technical Corrosion Collaboration, or TCC. And that Technical Corrosion Collaboration, is shown here, is something that the Office of Undersecretary of Defense ran, and they looked at corrosion problems. And there are a lot of words there, but there are 2 objectives that I can really summarize up pretty briefly. First is to develop technologies, advanced components, or products. So it could be knowledge, it could be processes, it could be materials or coatings that tangibly reduce the impact of corrosion on Department of Defense assets, right? And then the second is to produce these individuals. Again, it's back to the individuals with advanced education and skills that form the future core of the corrosion prevention control technical community within the DoD. And I would say like UVA is a big supplier of that. I would say at Naval Research Lab as an example, practically the entire corrosion, all the corrosion divisions are staffed with UVA PhDs. And so over the long run, it ends up being the individuals. Over the short run, yes, it's the component or the product. So the DoD personnel work very closely. The difference between this is that you don't give the university the money and say goodbye, I'll see you when it's finished. There's close collaboration, and there's collaboration often with colleagues in a DoD laboratory side by side. The university student is working with someone in a DoD laboratory, might intern there or spend a summer there. And then upon completion of the research, the institution is provided a product or they're provided a test procedure, whatever they need. So here's an example of that in a flow chart, and the level of effort and time, I guess I should put time on the x-axis. But the research institution doesn't play the primary role when the problem is identified. So the problem is identified over there on the left. And then the major player there is the DoD technical personnel. They're saying, gee, we've got a problem in this. It's longer term than we can deal with, and it's complicated. And so then the research institution takes over. That's during the period of the grant, let's say, and the research and technology takes over. But the DoD personnel, like I said, don't disappear. They just play the secondary role where the research institution plays the primary role. Then over on the right, what you see is the flip-flop occurs, the inversion occurs. The DoD personnel catch it, and they sort of catch the pitch, and then they catch it and they implement it. And then the role of the research institution doesn't disappear, but it goes down. And the situation goes back to DoD. So I won't read you this long list, and time's getting short, so I need to go through this quickly. So an example of that, a big thing, is accelerated testing. Everybody's interested in accelerated testing, always has been. It's a vexing problem. How do we accurately simulate atmospheric corrosion? For instance, is one of them you're concerned with for aircraft in the field. And then how do you do a life accelerated test that mimics what you have in the field or accelerates the same mechanism, but in short term than a 5 or 10 year exposure in the field? And so, that's a vexing problem. As you know, ASTM B117 is notorious for not matching the field exposures. The samples that come out corroded, they don't look anything like each other, right? So there's a lot of outputs there. You can see I've got them listed. You'll have these slides. I won't read those all. Not all those. Another one is a classic one. Is robust substrate protection for lightweight alloys, i.e. chromate replacement. And the question is, how does chromate work for corrosion mitigation? What single or combined strategy can provide equivalent protection? And that's a mouthful, because there may not be one drop-in substitute, as you know. And then one of the things that our DoD was really interested in, especially since they are worldwide, is are there situations like environments where the mitigation inhibitor doesn't work or the pre-treatment doesn't work? So one of the things they want to know about, as well as the good story, they want to know the bad story, like where does it not work? Do you get into the jungle environment or a desert or some dry situation or some very wet jungle situation where it doesn't work? And so those are two classic problems. So what did the university and the DoD get out of it? The university, I won't read you, same kind of benefits: sponsored research funding, new knowledge, student development, student internships, publications, etc., and knowledge generation dissemination. The DoD, they got the workforce development, they got the state-of-the-art research tools, and then they got better technological outcomes that are used in the field. And some of the chromate replacement strategies, as you know, are in the field on aircraft. They're actually flying on aircraft. An example is the metal-rich primer that is used that was developed for aluminum-based alloys. And those primers are actually, my understanding is that a couple of European air forces use those systems. So the last one is now that you got this introduction of the way some people do it, as far as industry and government, what about centers that try to do this? And how would you form a center of excellence? I'll tell you even about, in the closing minutes, about how we formed our center, which has been around for a while. And so now, the Center for Electrochemical Science and Engineering at UVA and it's co-directed by my colleague Rob Kelly and myself. And we've been the directors since the 1990s. The center is one of the premier centers. It's not always been corrosion, it's always been electrochemistry and materials. You can understand there's a lot of interest in batteries and recycling now, and we have a hiring for a faculty position, and I'm not sure that faculty member will look like Rob Kelly and John Scully. I don't mean as far as how ugly we are, but I mean as far as the mix of things that they do might be different in the new faculty member. It's someone that can work in harsh environments or in harsh situations. Harsh has lots of meanings to lots of people. So we've graduated over 250 advanced degrees since its founding in 1969 by Glenn Stoner, and we're proud of our graduates. They're all over the place, the DoD labs, the DOE labs. We have over 10 professors at universities that teach corrosion. And the scope of the projects range from fundamental studies, actually to consulting, to applied science and engineering, but also consulting. 8 faculty members are affiliated with it. I won't read them all, but you can see Beth Apila, she does the high temperature oxidation. Jimmy Burns here does the fracture. Giovanni Zangari does more electrodeposition and electrochemical synthesis, and so on and so forth. So it's a pretty big center. That actually cuts across, I should mention, a couple of departments. So our center is housed in the material science department, but it actually it's actually in several departments. And Gary Koenig is in chemical engineering, for instance. So our center kind of cuts across the department silo structure that you have. And then I won't read all these to you, but there's lots of different sponsors. Most of the acronyms I apologize for, but they're mainly U.S. agencies like NASA, it's National Aerospace, and most are, some are written out. Not all American, like POSCO Steel. We've done quite a bit of work with POSCO Steel and International Copper Development Association. Done some work with Petrobras. On the right, things that are more like short-term or consultancy project. So the left is long-term, the right side is short-term. And you can see that's a little bit more industry heavy. Sometimes they've got a problem. Petrobras has had a couple of problems that they needed us, but only for a couple of months until the problem is solved. The outputs from CSC, then fundamental research, personnel, tech transfer, service. So we sit on a lot of review boards and editorial boards, the Defense Science Board. We even played a role in the Space Shuttle Columbia accident during re-entry. I don't know if you remember that, the Space Shuttle Columbia, it burned up on re-entry, and there was a couple of corrosion questions there that they thought were very important. And so we play a role in these national panels. Lastly, but not least, product development. We've developed some products and some coatings and have some patents on some alloys, some new alloys. I mentioned all this project stuff and all this collaboration with industry and government, but I just wanted to point out that the workforce development is a big part of our goal. And like I said, over the long term, 20, 30 years out, the research scientist is the most important thing. And so the way I view engineering education and corrosion is in this pyramid or this triangle with the technologists and the inspectors and the maintainers, the people that know how to paint a structure properly with the proper preparation at the bottom, and then the corrosion scientists at the top, and the corrosion engineers somewhere in between. We also hope that in the light yellow, that the bachelor of science level engineer takes a corrosion class. And so that's a big educational issue for us is having mechanical engineers, for instance, take a corrosion class to avoid mistakes in material selection that might happen. And so to end here, just except for the thanks, I was going to say, how are some of these centers formed? Well, it seems like the Fontana Corrosion Center, which is out of the Material Science Department at Ohio State University, they kind of came out of the left. UVA, UMIST, the Corrosion and Protection Center at University of Manchester came out of the Chemical Engineering Department in Manchester, yes. Graham Wood got a grant, and he was the first chair professor that they had in the UK in corrosion. But they were a part of the Chemical Engineering Department at UMIST. And now it's a part of the Material Science Department at University of Manchester. UMIST is University of Manchester Institute for Science and Technology. So it's actually stayed within the department, but gone from chemical engineering to material science engineering. So the usual structure is that it comes out of the engineering school. The thing there, what does it take? It takes an industry or government sponsored chair professorship. Like you have to prime the pump, so to speak. It takes somebody to come up from industry or government and convince the dean of engineering to fund a faculty position, and money helps, right? And so in the industry, we've done it several times by having an industry or government partner that will support faculty for 1 or 2 years, and then the dean will take it over, and the School of Engineering will take care of it. So our faculty are on 9 months appointment. That means 9 months are paid for teaching, 3 months for research. And so we can sustain that in that kind of formula. And then, of course, the high-performing faculty carry their own weight within the university. So the high-performing faculty can go to the dean and argue for a position. That's what Rob and I did to get someone in harsh materials and harsh environments. We convinced our dean to hire a younger person because we're getting old, right? We're getting old guys. And then to sustain that, really the faculty need to get tenure. They need to be promoted, and you really need to secure some kind of sort of center funding. The other model is like the model of Curtin University in Australia. In that model, they have engineering departments at Curtin, such as mining engineering, chemical engineering. Not showing them all, but they also have centers of excellence that are outside of the department structure. So the Curtin Corrosion Protection Center, the Center of Excellence at Curtin University, is not funded is not aligned with the department. Now they do grant degrees. Students get degrees in chemical engineering, but the Curtin Center is not really is a standalone center. So that's where I'll stop. I think I've gone plenty of time here, but I just wanted to thank you for your attention, and in the time allowed, I'll take questions. But if I can't get to your question, you can email me here. Thank you.
Thank you, John, for the very lucid and comprehensive, I would say, description of the center formation and how it runs. Can you come on the screen? It's okay for you? John, can you unshare and come to the screen? Yeah, thank you. Yeah, so hope you're okay with some questions. Yeah, thank you.
Yeah, my pleasure.
Yeah, thank you. So
Thank you.
let me invite the participants. Any questions? Any of you? Yeah, please.
So,
Can you come forward?
so you can ask and this one.
Okay, yeah, please tell me.
So that CESC and I think in the presentation we see one policy that is depicted on USA corrosion policy somewhat I see. So just a clarification whether this CESC is supporting drafting that policy or under that policy the CESC has been constructed.
Okay. So the question is related to the corrosion policy that the defense, you have projected one screen, the corrosion policy at the defense level, I suppose, at the national level. So how does it evolve, and how does it get implemented?
Yeah, the implementation, is sort of a handoff. It's a handoff. We provide, we provided the coding testing, for instance, and the formulations, and then they go really to a vendor like AkzoNobel, and they make the coding, and then they decide whether they might even do more testing. They might decide to test it in Hawaii, which has 5 different environments, or they go right to the phase of putting that on a piece of equipment. And so basically in that structure that you saw, there's a period where the university does most of the work, and that's more at the coupon level. And then there's a period where they take that, and for instance, in that example, and apply it to the field. But I should tell you, like, another way to do it, depends on what the outcome is. Say that it's a testing protocol. Suppose we say that, well, the way we test coatings is not the right approach for metalworks primers. The traditional way we test coatings, even things that are my favorites like electrochemical impedance, metal rich primer, impedance doesn't tell you all that much. And so maybe it's a test protocol. Well, what happens is that goes to DoD, and the DoD might make a sort of a military specification for testing. So they're not taking the component so much, they're taking like the product is the way you decided to test it. And that's what we do. The metal rich primers are tested in a different way. We use different approaches. We use some material science approach. For instance, you can use X-ray diffraction, and we can do X-ray diffraction. So the pigment's used up, the diffraction is going down. Or if they're converted from metal to oxide, they're converted. So they might write that into a procedure that they give for DD. So they convert that into something that they use. In that case, a document.
Yeah. You okay? Yeah, please.
Yeah, great question.
Thank you.
Can we have a thing asking as the world is going towards as the world is going towards the green hydrogen energy based economy in future, so how the corrosion management aspects are going to the change with this in respect of the green hydrogen economy and also how the the latest technologies like artificial intelligence are being used or they are supposed to leverage and improve the significance performance of this corrosion management in future.
It's a composite question, John. I just split the question into two parts. One is we talk about I think there's next speaker we're going to talk about also. But anyway, so there is, we talk about green hydrogen or hydrogen economy we talk about. The role of corrosion scientists and engineer in looking at this technology. What role do we play? The second question is that what level of AI ML now is to take care of the corrosion related activities?
I'm sorry, I didn't get the second question so much.
The second question I repeat again is, I mean, the development related to AI, artificial intelligence
yes.
and machine
Yes.
learning,
Yes.
and to what extent the corrosion engineers or scientists are equipped to solve the problems.
Right. Well, first of all, I'll say on that one that you can't use ChatGPT. We've had this discussion, but I think Nick Burblis, someone asked ChatGPT what's the best for chromate replacement, and actually, well, they got an answer. But remember, ChatGPT only their database only goes to like 2021, so one has to be careful. No, but that's I'm being somewhat funny there. I think there is a role for artificial intelligence. We're pretty heavily involved in material science in general, just like in medicines and drug. There's a role because there's so many. It's hard to see the relationships. There's so many variables, as you all know, that affect corrosion. So we are working with it. One of the biggest problems that we're seeing right now, of course, I'm interested in corrosion-resistant materials and have been working for several years. Even a little bit with Narazi Sridhar, looking at what are the factors, what are all the factors that determine, say, like the passive current density. And one of the problems that we have right now is the data quality. The data is spoiled because, as you know, a lot of corrosion properties, like the passive current density, depend on the way you conduct the test. If you run a potentiometer with polarization. So one of the things is data cleansing and data quality, and the data is polluted because you're comparing really things where the paper does that you mine. So we're really at the starting point. We're using large language. We've written a few programs with our gifted undergraduates, these large language protocols where we can assemble huge databases and read like 100 papers. So we can get the data in. The question is the quality and how so that's right where we are with the CRMs, in my opinion. Others might have a different opinion. I mean, there are success stories, there are correlations that you can't see by just varying the chromium content or something. There are all kinds of connections that start to be revealed. And what those do, I think pragmatically, what they do is it's not new science, it's not new engineering. It creates areas, regions where you should focus your resources to do testing or research. Like if there are gaps in the data, you might hit those gaps. And right now we're trying to do this for stainless steels. And one of the problems we have is data quality. As I mentioned, we resorted to generate our own data because we could control it and we could report all the conditions. And we seek to fill out the space to train the models, basically to fill out data in areas where data is sparse. Okay, so yeah, that's that one. And the first question was, I forget again, refresh my memory.
That's about the green hydrogen we talked about.
Yeah, oh yes, the
And,
green hydrogen. Thank you very much. Yes, you know, we're in discussions with coating companies. For instance, you know, coatings, they would, you know, there will be corrosion issues. You know, there will be the solar energy electrolysis of water that will have all the host of problems associated with that. Solar panels, I will say that there are some things that come into use that are actually not very well studied as far as their degradation. And you know, solar panel degradation is a corrosive phenomenon. And so there are people that have studied, like the San Diego National Labs, Eric Schindelholz has studied solar panel deterioration. But I can say that there's a big interest and concern for hydrogen transportation. And coating companies have approached lots of people in the corrosion field about, if I repurpose a pipeline, gas pipeline, high pressure gas pipeline for liquid hydrogen, what kind of coating as a permeation barrier do I need on the inside of that to keep hydrogen from being absorbed? And so it's a whole new realm of coating design where you're exploiting probably one strategy is to avoid uptake and permeation, and then what coating would you want to do that? So there's going to be corrosion research, right? Always is.
It's a very interesting topic. I mean, it opens up a lot of avenues for corrosion people to do research. Yeah, thanks for the perspective. I think we are running, I mean, we are almost close to the time. I just want to ask a question, if it's okay. See, we have a different kind, I mean, you might have it. In India, there are, I mean, we have students who work in the organization and carry out their doctoral degree, and sometimes they do their master's degree. So, do you have a similar kind of model existing there? How, in that case, the university and the industry partners work in shaping the graduate students coming from industry, not a full-time, as a part-time student? I hope I have made the point clear.
Well, we at UVA right now, we have a small professional master's. A lot of universities have gone to it's a money-making operation, have gone to a large professional master's, and that's a large source of revenue for the department. In those situations, you know, there are places where it's remote. There are places where people come in for a semester. There are places that are completely on campus or completely on their programs and MS degrees that are completely on grounds. There are schools that are thinking about what I call certificates. Their certificate is this. It means like if you have to take 10 classes for a master's of materials engineering, which is typical, 10 classes is typical in the US, then, but no research, only 10 classes, then you can take a certificate, like 4 classes. People can basically build up to the master's. They can take a group of classes, like the first 4 and the second 4, you know, and then the last 2, and they can take classes sort of in a bundle, you know, like this, and they can either leave with a certificate and say, well, I've got a certificate in cathodic protection. We're not trying to duplicate what the societies do. So that's the master's degree, and there are some places historically. There are places that did it one of the most famous is University of Manchester, the Corrosion Protection Center. Has to this day has a large master's program, and so does Curtin. We don't have so much at UVA. We really, the gem of our material science department is our PhD program with over 100 PhDs. So we tend to focus most of our energy on our undergraduate program, which has a corrosion class, and a lot of people are interested in it. It's called Corrosion Batteries and Fuel Cells, and our graduate classes. So that's a PhD program. People go now straight from the bachelor's to the PhD. So that's about a 4-year program, bachelor's to PhD, sometimes 5 years. And does that explain how we do it? That's kind of our approach to it. A little bit different in Europe and in Australia.
Okay, John, thank you very much, and I thank on the behalf of the organizers and the participants and myself for giving a very nice overview of the university and the other agencies' interaction in terms of forming good center of excellence in corrosion. Thank you. We hope that next time we'll see you in person here, and thank you very much. Thank you very much. Thank you. Bye. Thank you very much. Thank you.